Thanks so much, Katerina. Thanks to the organizers for the invitation, and thanks to everyone for joining for this last talk. So my name is Pooya. For those of you who have heard talks from me, I usually talk about quantum architecture. That's the stuff I do at 1QBit. But today I want to talk about a project I've been doing at the University of Waterloo with my students and postdocs. So part of the stuff I'll talk about is a last year paper, ICML paper with Arsalan Motamedi. And then there's a draft that I can, it's very ready. I can share privately if anyone is interested in. It's with Maria Sobchuk, Sharon Lee, Arsalan, Gracia Castellazo, and Alaisha Yaqi, who is a collaborator from National Research Council at Canada. Okay, so this talk is a little bit controversial because I will talk about classical problems. And it's a lot more computer science flavored. So there will be like order and complexity, but all those complexities are gate counts and Clifford plus T. So really the goal is eventually to write code and do detailed resource estimations. But we had to do a lot of interesting theoretical groundwork that I hope you enjoy hearing about. Okay, so my ultimate goal was kind of understanding what problems can we solve with quantum computers, not just small quantum computers or near term, but is it, for example, true that really if you want to get substantial quantum speedups, then we have to do something like simulation of an inherently quantum system.
Sorry, please.
Yes.
I have a question.
Please.
Don't we know the answer to that before your talk? Because
No, I'm hoping that I will convince you otherwise than what you already think.
Prime number factoring.
Yes, I will talk about that.
And that's not a quantum system.
Yes. So I will talk about that. Yeah, exactly. So it will come. It will come in a second. Yes. So I agree that the motivation motivation of building quantum computers has been to simulate quantum systems. But as Matt was saying, for example, we know of factorization that is not a quantum simulation of a quantum system, but it's actually one of our best examples of quantum speedup. And by the way, it's not known whether factorization is NP-hard, so we don't exactly in some sense, that is not a provable speedup. But people in computer science community have tried to understand what about short factorization make it so that you do have this really nice speedup. This paper from Aronson and Ambanis was very inspiring to me when I heard the talk about it. And then there are sequels to this line of work where they ask, if you're given a circuit that encodes a Boolean function, then what structure does that Boolean function have to have in order for you to get super polynomial speedups? And then, so this line of work ends up concluding that quantum Fourier transform is quite critical in those types of speedups. And the fact that you're looking for some periodic structure in integer rings is the reason QFT can really exploit this problem. Okay, so but if you talk to classical machine learning optimization people, they don't talk about Boolean functions. They usually talk about continuous functions. And then usually the way you find hardness of the problem is nothing about the stuff that you see in this type of explorations. Usually you have things about convexity, non-convexity. Those are the ways we understand hardness of continuous realm problems. Okay, so and then my question is, I want to think about quantum computers as like normal computers that have memory and you can put bits like float point representations of numbers in them and then do stuff with them. And then if you think about it that way, then you really want to talk about properties of continuous functions as continuous objects. Okay, so what properties of continuous functions can help us understand whether we can maybe prepare them on a quantum computer efficiently or not? Okay, so this is not where I started. I was just trying to understand, if I take things that are known as quantum algorithms off the shelf and and just like throw classical problems to it. What happens, what goes wrong, do I get speed ups, do I not get speed up? So I looked at, I was interested in PDE, quantum ODE and PDE solvers, doing quantum linear algebra. And then I knew that classical machine learning people are very interested in solving diffusion equation. One reason is something called energy-based models. There you solve the diffusion equation for some potential. And the way classical machine learning people do this at very large scale, that gives you really, really interesting models, very smart models, is they run something called Langevin dynamics, which is a stochastic differential equation like this, which is kind of what Brownian motion comes from. Okay, and then there were sequels to these type of models that then really became state-of-the-art image generation, which are called diffusion models. And diffusion models, you also simulate some diffusion process, and the trick is you kind of learn how to revert the diffusion with another stochastic differential equation, and then this was how state-of-the-art image generation kind of started a few years ago. Okay, so we know that there are papers about solving heat and diffusion-like equations on quantum computers, and so if we try to apply it to this problem, what happens? So the stochastic differential equation is not what we want to solve on the quantum computer. There's something called Feynman-Kac formula, which lets you translate a stochastic differential equation into a partial differential equation. And this partial differential equation is second order. It has these kind of diffusion terms and has some linear drift terms. Okay, so this is the integrator. And the reason this translation holds is because of something called Kolmogorov equations. Basically, they show how the marginal distribution at every point in time evolve when you apply this generator to it, and then that's how you extract the second-order differential equation to every stochastic differential equation. So no one in classical computing does this diffusion like the PDE. Usually you run the SDE on GPUs. And then I was asking what happens if we were to solve the PDE. Okay, so we are either solving the long time, like we just apply L for a really long time, this generator for a really long time on a density function. And then if you run it for a long time, it will basically mix into the Gibbs state of that potential that was given by the drift. Or you just find a steady state of that dynamical system, which is solving this time-independent equation. So this time-independent equation, at first I thought is really bad to solve. And we were first trying to do this. And then there were updates to this. Okay, so I was trying to solve this equation by just linear algebra. And so what happened was, yes, so this is, yes, go ahead.
One question, can you go back to the previous slide? So you just say that set L rho equals to 0 is very easy to, so it's very difficult to solve.
Yes.
But if you have some like blocking encodings of this L, then you can just use QSBT.
Yeah. So the newer methods that try to do Gibbs sampling with this idea, they try to do singular value thresholding to get the 0 eigenvalue. Yeah. So what we were doing at the time, we were just trying to do the long time limit of this. I will come to the reason we were doing that, and then what was the improvement that happened. Yes, nice, great question. So the idea is to solve this partial differential equation. You're given access to some potential, with some block encoding or some maybe bits oracle is worse. Probably a block encoding is what you hope that you have, and then you want to solve this equation. Okay, so the idea was to take this generator, as you said, linearize it, and then try to solve this ODE. So what Arsalan showed was that even if you try to do this, you run into the same curse of dimensionality as classical differential equation solvers. Basically, if you want precision epsilon, you need to make a gridding you need to discretize space to 1 over epsilon order. And then that means you get a mesh that is 1 over epsilon to the d big, which is also the reason classical differential equation solvers have a problem. They have this curse of dimensionality. So quantum linear algebra doesn't really get rid of this. So what can you do? And so Arsalan made a very interesting observation that if we turn this U, and if we do a Fourier transform on it, then we can look at the Fourier grid instead of the spatial grid. And then in the Fourier grid, if the solution is analytic, then we do actually end up with very, very few discretization on the space. And then that gave us a high precision solution, okay? The problem was that we still have this thing called the Poincare constant, which is something like the condition is related to the condition number of the generator. And we weren't getting rid of this because we had to run it for a really long time. There was an improvement to this paper last year that showed exactly what you were suggesting, that you can solve this equation. But even if you solve this equation, you still end up with a CPI order complexity. But the reason this paper got this root CPI was a very interesting decomposition of this operator. Okay, so but I was talking about, you know, so this is really the scaling, state-of-the-art scaling. But why is it true when you have some, you know, regularity condition like analyticity?
Yeah, what do you mean by analytic?
Yeah, so analytic functions are the ones that their Taylor expansion converges. And that's very rigid. Like smooth functions aren't necessarily analytic. Okay, so you know, exponentials, trigonometric functions in the domain that they're defined, they're all analytic. But you know, you can have smooth functions that aren't, as I will show in a second. Nice, yes?
Is there work that needs to be done in terms of linearizing? Like, is that an easy task in this case?
Yeah, so I will talk about the exact circuit that is the block encoding of L. And then it's actually surprisingly very efficient. I was expecting that this whole thing is going to be like, you know, tens of thousands of logical qubits at least, but it's actually a very small circuit.
But you're starting from a problem where it already looks like L rho is equal to something, yes? Like you already have it in this form. You don't have to.
Yeah, so you kind of, like the whole idea is that you discretize space and time, and then you just get a big linear system, and then you have to invert the brightness, yeah.
So when you say analytic, do you mean a real analytic? Also, does that mean both for the time and space?
Yeah, so in this case, you don't have to do the time because this drift is time independent. If you wanted to do diffusion for a finite time, usually your drift is a field that is changing over time. So if you're doing some non-equilibrium dynamics, then you need to solve time-dependent versions. But because here I'm only showing examples in equilibrium dynamics, it's a good point, everything ends up being time independent somewhat, yeah. Yeah. Yes?
Before we get too far from the diffusion models,
yes.
How much work is there left to do to connect the, say, like the quantum algorithms that you're exploring here to, like, you know, computational problems that are coming from applications?
Yeah, so I will talk, for example, about protein folding as one of the things that I'm very interested in because people try to apply diffusion models to them. So we'll see if quantum algorithms can help with folding problems in molecular dynamics. Yeah. Okay, so right. So what is this critical role of QFD in what we were showing? So you want to do some amplitude encoding of a real function. And so X is a register, maybe a 16-bit register, something like that. So you don't have infinitely many states to encode. So you're always going to be in some finite discretized space. Okay, so what happens when you have if you were given this, or maybe instead of being given this, if you apply Fourier transform, what you get is the amplitudes become the Fourier transform of the function f. Not quite, they become the discrete Fourier transform of it. So what you really want to do, if you want it to be completely faithful, is you want to do the Fourier transform or Fourier series expansion, which is on all of the infinite lattice. It's on all of ZD. So it has components with your function, depending on its Fourier transform. It can have very highly oscillating modes, and those will be high f omegas for large omegas away from the origin. Okay, so these Fourier coefficients are calculated through Fourier transform like this. But that's not what we have access to on a quantum computer. And a quantum computer, we have access to discrete Fourier transforms through QFT. So they will do the same thing, but not on all of ZD, but only on a finite lattice. Okay? So then the question is these discrete Fourier transform coefficients, what is their connection to the actual Fourier series expansion coefficients? And that is this equation that is really important in our work, which is called the aliasing sums. And so the intuition is that, if you take omega in some bounded lattice, then you have to look at all translations of it in the other regions of the periodicity. So this is what this sum index looks like. And then if you sum all of them up, it will be the actual Fourier coefficient. So you have the contribution from the point that you had access to, but all these other points you didn't have access to, and they add up to create an aliasing error, okay? So in order for the first f omega, the one that is in my fundamental region, to be a good approximation to the Fourier coefficient, what you want is you want these coefficients to die out really fast away from the origin. If that happens, then I can forget about these other indices, okay? So this is a different way of defining analytic functions. Analytic functions are the ones for which the Fourier coefficients decay exponentially fast. So this is equivalent to that Taylor series converging, absolutely, right? So analyticity, the reason analyticity was important was you want these Fourier modes to decay really fast. And then we realized that we can really, really generalize this. So all these Fourier coefficients, in fact, if you only have p times differentiability, they do decay really fast. They only decay polynomially fast. If you have Lipschitz, like something like Lipschitz condition, you also get, some more exponents in this polynomial decay. If it's only continuous, we know that it decays, but we can't associate a rate to it. So it's unfortunate that with continuous functions, this doesn't even hold. For analytic functions, it's the one that we had, the old result, which is an exponentially fast depending on this radius of convergence of the analytic function. So the radius is like if you think of the analytic function on the real, like as a real valued, real variable function, then you extend it to the complex domain. There is like a tube around the origin for which the convergence happens, and then that's the radius. So basically, the first time you get to the pole, a singularity of the function, the radius is up to that point. So if it is globally analytic, then this radius is depends on the box. It depends on the radius of the domain for which you're defining.
My spectrum could have a continuous set of frequencies that are all you don't just have one pole, but you can have a whole distribution of poles that are connected.
Okay, so that is the role of periodicity. So if it is periodic, then the spectrum is discrete.
Yep. Yep.
And then instead of the Fourier transform, I can do Fourier series, which is only on the integer lattice. Yes.
And what does the omega sub infinity mean?
That is the infinite norm, which is just the largest, like omega is a bunch of frequencies, take the largest one. Okay, so then there is this class of Gevrey functions. So Gevrey is a French mathematician who showed that there are lots of exponential decays. So you can have slower exponential decays, but there are still exponential decays. And then most smooth functions, most infinitely differentiable functions, are in some S-Gevrey class for some S. So S equal 1 is exactly the analytic functions, and then larger S, larger than 1, means it's less smooth or less close to analytic. And then there is a whole hierarchy of these functions, and most non-pathological smooth functions are S-Gevrey for some S. Yes?
When you say most, you mean in the measure theory sense?
No. So I meant, actually, I don't know. Maybe that's as well. But for example, to construct a smooth function that is not S-Gevrey for any S, the way I know a construction of is that I will pick the Fourier coefficients one by one in a way that it rules out any exponential decay. And then that's the construction. So I don't have like a closed formula for that function. So it's actually hard to, there are smooth functions that are not as trivial for NES, but they aren't the typical ones you encounter.
Yeah, they're exotic.
Yes.
Like you had to take a limit there. Or something.
Exactly. Like I had to do some weird construction to find it. So for example, this thing is called bump function. So it's, it's the function that is an exponential. It's very nice analytic, it's an analytic formula as you see. And then when you get to 1 and minus 1, you want it to be all 0 away, okay? So if a function is completely constant in some part of its domain and it's analytic, it has to be constant everywhere. It cannot pick up, right? Like the right derivative here is 0 for all orders. So it can't pick up. So for these functions are not analytic. So this one is Tougevrey. Okay, and then these bump functions are very important because it gives you access to like local properties, and you can do important things with them. So it was not a good thing that we were limited to analytic, but now we know that actually like this whole hierarchy of smooth functions have these nice decays. Okay, so this is just to represent a function with like a qubit-based register. I want to now approximate how other properties of it decay. So if this decay is really fast, then the tail of it is very small. And then here, En is this truncation error. So if I replace the function with this finite bandwidth truncation of it, the error decays according to these numbers. Okay? So I'll come back to this En when I show you the result. Okay, so right, so let's say our example is we just want to solve this general linear differential equation. And so alpha is a multi-index. So U is d-dimensional differential equation. Alpha has d numbers in it. And then there's some coefficient functions. So again, the idea is just take the generator, linearize it, use a quantum inversion algorithm. Okay, and then what I said was that we were hoping to perform Fourier transform, differentiate, and invert, but we don't actually have access to Fourier transform. In brackets, if this was a continuous variable computer, we did. So, interesting stuff can be done in an optical, for example, setting. But what you have access to is quantum Fourier transforms and these discretized Fourier derivative and inversion. Okay, so what are these things? So in Fourier domain, differentiation turns into just shifting the omegas. Like you just multiply by another omega, so differentiation just maps to this operation, which means that I just need to make a diagonal of multiplications of these numbers. Like, so if this lattice goes from minus n to n, then you have these numbers, d of them, and they get multiplied by the order of derivative in that variable. So this is just a diagonal element, and then there's this I, which we can take out, and that's fine. So you just need to create something that looks like a bunch of diagonal integers. Okay? So this is a efficient block encoding for this operator that I was showing. What we do is we swap. So we have these x1 to xd registers, and then we swap them into a line in which we apply differentiation. And we don't apply the d-dimensional differentiation, we apply a single partial derivative, which means that the diagonal just goes from minus n to n, and there aren't d of them. So this is a very simple diagonal. It's just literally minus n plus 1 all the way to n, one Fourier transform inverse. That's this gate. And then you swap into this line, and you apply derivatives, and you go back. And this does all of the LCU of all those differentials because of these registers that have the indices in them. And those are the controls, okay? So then the whole operator, maybe you need something like a QROM to load those indices and then do this thing that I was showing you, the swap network, and then compute the QROM, and then you can you can select the right coefficient as well, and then this will be the full LCU, okay? Right, so because of that, I can give you actual gate count instead of just query count. So the result, the observation we made for the differential, so how does the error of the differentials change as you do this truncation. As you see, this is the culprit for the curse of dimensionality, and it's still there, because if I have n to the d points and I have a tiny error on each of them, they get multiplied by n to the d in error. So this truncation error, which is the size of the tail, if it is decreasing faster than this, then I can bound this error. And then that happens for Schivry functions and for analytic functions, but not for smooth functions. So for smooth functions, this is always getting dominated by this large coefficient, but for smooth classes, it's getting suppressed. Okay, so this shows that the number of, the size of this discretization can be bounded by log of 1 over epsilon, and then depending on the s, you get a power of s. Okay, so then you can get a full gate count, because I also showed you the block encoding for the operator. And so this is a giant formula. I will show you a simplified version. So for example, note that s is equal to 1 if I knew the solution is analytic. These numbers, I won't define them right now in interest of time. But basically, I have something that grows polynomially with d. This denominator is basically our well-conditioning kind of parameter. You have to decide like what's the, what are the smallest non-singular values you want to keep when you do the matrix inversion. And so this is kind of like this is something that in applications you probably know exactly what it is. It might be bounded. So I will show you an example. And then the qubit count is really nice. It's actually linear in D, because it was really those D registers that I was showing you. And then if you can get rid of the QRAM, it's pretty much that. And then you have just logarithmic, qubit count for the ancilla and the bit register itself, the size of the bit register. Okay, so yes.
You mind just redefining what the N and S are?
Yeah. So big N is the truncation threshold for the Fourier indices. And so that means that if I'm truncating up to N, then a register keeping a point X needs to have log N bits, or qubit, log N qubits. S is a measure of how close to analytic it is. If it is 1, it is analytic. If it is larger than 1, it's less close to analytic, but it is smooth. And then like J is the set of indices. Usually there are only few terms here. And so this is the set of all the indices that the differentials are from. Epsilon is the precision, the L2 precision of the solution, a target that the user defines. Yes?
I think you said this before. What gates are you counting here exactly?
This is Clifford plus T.
So Clifford's and T's together is...
Yes.
Okay,
Yeah.
interesting.
Yeah, it's actually very, so I'll show you, most of these things are bounded, so they go away. The scaling becomes actually really nice, both in the circuit size and the qubit count. Yes?
So compared to the classical spectral method, is there any way we can see where the advantage or possible advantage can be obtained?
Yeah, exactly. Yeah, that's what I want to get to in the next few years. but yeah, I will basically, ultimately you have to do write the code and do a resource estimation. That's what we are trying to do. But if you don't do these things, these circuits will need tens of thousands of logical, or hundreds of thousands. This is about how to actually even solve problems efficiently that look classical or look like differential. Yes.
What? This is Lex's question. He's too embarrassed to ask it. What is that seal?
Yeah. So this is the largest. Imagine this is the largest G value. This is the largest index. The order of the differential equation is cap J, and then cap G is bound on the G coefficients. And then this is the number of indices. Yeah.
Yeah. So what is sigma mean
Sigma min is, so you, because it's the discrete spectrum, you will, if you know the smallest signature, then you do that. But usually, for example, if you're doing quantum singular value transform, you just decide a cutoff that from there lower, you consider it as 0 singular value, and you don't invert that part. Okay, so it's kind of like it's kind of a precision, but if you know your differential equation, you might just know a bound for it.
But then this sigma mean will be related with the CPI, right?
So here we're not solving the Fokker-Planck equation. We're solving a general linear differential equation. But if you did, yes, it will be. If that was the equation, then sigma min is probably, I don't know what is exactly the, but CPI is more like, because I'm taking the condition number and I'm bounding the numerator, like the sigma max is already kind of bounded in these coefficients. There's one sigma min that is left that is shown down there.
So basically, this whole part will give you the condition number.
Yeah, this part is condition number divided by sigma min, because even if you do QSVT only, there is a 1 over sigma min there, which is a decision you make what 0 means. Yes. Yeah. Nice. Okay, so all right, so in applications, that result becomes event. So this is what I started trying to do. So we're trying to solve Schrödinger's equation, but just as a classical PDE, okay? So there's this Laplacian term, and then there's some potential, and then maybe there are a bunch of electrons and nuclei, and then there's repulsions, or like, attractions to the nuclei with discharge, and then there are repulsions, Coulomb repulsions between the electrons, okay? So that is as far as I understand, that's the Schrödinger equation people write when they do, simulations in material science. So here, the Laplacian, that J bound is just 2, because these are degree 2 equations. And then this is very simple. The block encoding is even simpler than what I showed you. So this is even the simpler block encoding for the differential. So this is the total gate count, which is in the order of log 3, but dimension to the 4. And then the total qubit count is linear ND, with a log 1 over epsilon. So like if you solve really low dimensional problems, these are tens of logical qubits maybe. Okay, so the problem is that the solution is not differentiable, because if there's collision, like if the electron is exactly at the position of the nuclei, then these potentials are infinite. They become plus and minus infinite, right? And the solution to the Schrödinger equation, like the wave function you get from solving this, is continuous, but there are cusps in it. So it's not differential. It's not even one differentiable. Okay, but then I found that people do something about this that is called Jastrow transform. So you actually multiply by exponential of these terms that are dependent on these charges, and then that gives you a new differential equation. After that transform, H becomes some H tilde. And for that one, it is smooth. And then I can apply the result that I was showing you, the big formula in the last slide. So you get some really nice actual gate count in terms of the charge of the particles, the number of nuclei, the number of electrons, and this log 3. And then for a point of comparison, this is the complexity for the full circuit versus 1 over epsilon to the power 3m, because 3-dimensional for m particles, and then there are 3 dimensions for each of them, so the PD dimension would have been 3m. The other nice thing about it is that instead of doing this kind of pipeline, you can do it for like k-dimensional reduced density matrices. Like if you do the single particle approximation, like Kohn-Sham equations, then this complexity is 1 over epsilon to, I guess, the 6, because 3 dimensions and then density function, so 6. And then you get something like a 6-tick speed up in reading out classical numbers from this. So basically doing it for the hierarchy of KRDM, density functional simulations, I think you get different order polynomial speedups. from doing this, assuming that you're still reading out some classical numbers in the end, because otherwise you have an exponential speedup. Yes.
What is the D here? D.
What
So
is?
in your total gate count, what is that D?
Oh, yes, sorry, this should have, I should have made that be 3M. Yes, yes, nice, thanks, I'll fix that.
And I've lost track of what you mean by solving here. Is it preparing a state in the kernel?
Yeah, so we prepare a state, an amplitude encoding of the density matrix.
Like the kernel of something in the kernel of the operator?
No, we want to invert the part that is invertible. But what you do is you prepare a state where the classical numbers that are the probability, well, it doesn't have to be classical. What has to happen is that for every state x in the x register, the value is psi of x. The amplitude is psi of x. So it's the sum of psi x ket x, and psi is the solution to h psi equal some source on the right-hand side. Does that make sense?
Oh, okay, so you're inverting.
Yeah, so we're still doing inversion. And the goal is to find an amplitude encoding of the test function. Yeah. Yes.
So what does the capital P means again?
Capital P is number of nuclei. So number of electrons, number of nuclei.
Sorry, just
Yes.
to follow with the dumb question. If eta were like a delta function, you would be finding a Green's function.
Yeah, that's a good point. So if this was 0, then I can't invert. And that's the steady state Schrodinger equation. Yeah. But if you had some source because you're doing, I don't know, linear response or something like that, then it becomes invertible and this applies. Yeah, so I think the pipeline is that you solve the ground state problem, you get the ground state, but you don't read off classical numbers from it. You use it as a resource state to create those delta gates because you kind of consume it as you build, usually you, as far as I understand, you build this resource term from some ground state problem, right? So you can solve the ground state problem with some other quantum algorithm, and then the state you prepared, you just consume it to solve this PDE. Yeah. Yes.
Wait, sorry, I guess this is going to be a really dumb question. What information are we actually extracting from the system? Because it seems like this is just a method of preparing a state.
Yeah, so then you can do whatever.
Two-point correlation function or something.
Exactly. Like, so when
So
you
it's
do
just
these
state
simulations, then you want to read off some observables, for example. Then you have to do further stuff, like you have to do mean estimation or things like that on that quantum state.
So for this guy, simulation of an atom, what would we be? Are there any interesting observables here that people have looked at? Like, I don't know, maybe we're looking for the island of stability or something.
Yeah, so I think this is a very general way of talking about, like, when you want to understand the electric properties, photonic, thermal properties, like when you do material science simulations, you have these lattices, lattice models for the material, and then you need to find some numbers, like classical numbers. But the method is trying to build the density matrix first, and then get some statistics from it. So here we build the density matrix as a quantum state, and then if you want to read observables from it, then you will have to do more measurements. Yeah. So then, if you do that, then the whole end-to-end complexity is more like order 1 over epsilon instead of logarithmic in 1 over epsilon. But you still get a polynomial speedup because you still aren't scaling poorly with dimension. Yeah.
Sorry. So what is the quantum linear systems algorithm that you're?
Here it's quantum singular value thresholding, a quantum singular QSVT based linear system. So, yeah, this was helpful because it was allowing me to analyze the error in the block encoding, and all of that is easy to take into account in these coefficients. Yeah, if you did something like the adiabatic based, I think the big problem with it is that then you have to prepare the resource states as many times as you do the inversions, as you do the adiabatic transitions. Whereas in QSVT based, you start from the eta state and you just really apply the block encoding and some phase gates and block encoding and phase.
Amplify.
Yeah, exactly. It's actually a very short circuit this way. Yeah, a very low number of qubits. It's a small circuit, but it can be as long as you can make it. Okay, yeah. So any more questions on this? Yeah, so I want to just show you a couple of other applications we are looking at. So for example, the XY Hamiltonian energy, a classical XY Hamiltonian energy, is completely periodic because you are looking for a periodic degree of freedom. And you can try to solve these types of models with these algorithms because they work really well for periodic stuff. And then, as I understand, these things can be generalized to some models in classical field theory. And then the other thing that I said I will show you just as a kind of outlook is, so one of my students is also working on solving torsion problems in molecular dynamics. So we learned about these things we were in ICML because of the other paper, and then I saw this paper as one of the talks in the same conference, and then I realized they're applying diffusion with periodic boundary conditions, and I was interested in what they're doing, and then I realized these are what people do for protein folding. And in fact, the data sets that machine learning people use, they have maybe up to 5 torsion angles in them. So this actually becomes a 5-dimensional PDE for us, really tens of qubits. But you can have more complicated numbers, but in a lot of tests that training data sets you actually have very few torsion angles. Yeah, so I guess we can wrap up. So
I actually
yes.
want to, I'll let you wrap up.
Okay,
Sorry.
I'll conclude and then I'll take questions. So so I think I tried to convince you that the hardness of preparing these continuous functions have a very nice relation with the amount of smoothness of them. And this gives us insights that lets us think about quantum ODE PDE solvers in applications that are low-dimensional differential equations, but you can still get interesting quantum speedups, possibly. And then the one that I was showing you are these pipelines that, even the classical approximations people do to get to single particle approximations or KRDM approximations, I think all of them are good candidates for using these quantum linear algebra methods on them. And then I was showing you a few different application areas that I don't know these areas, so I'm looking for collaborators to write the code for them and talk about them. So if you're interested, let me know. And that's it. Thank you.